There are many candidates with the dark matters with the various mass ranges, from the ultralight, mass scale, and the light dark matters, including the hardened one, and the typical mass scales given by the GB to the TB, including the WIMP. And in the previous video, we talked about the heavy dark matters. The typical dark matters mass is given by the GB to the TB with the WIMP scenario. But in the subelectron bolt, which is motivated by the axion scenario, the dark matter behaves like the wave rather than the particle. In this mass ranges, the dark matter is sometimes called the ultralight dark matters, briefly ULDM. And also there are other benchmark point, Bose dark matters, with 10 to the minus 22 electron volt to explain the dwarf solitonic core. In this mass scale, the corresponding debris wavelength is extremely longer than the interparticular separations, and the occupation numbers are larger than the one. So the dark matters twist as a classical field and the wave. There are several characteristics here, which comes from the build and the build gradient and the coherence plane wave. And such a classical build description is varied when the occupancy number is very large. The debris wave length corresponding to the given mass scale is larger than the interparticle separations by calculating the mass around the dark matter's local density and its velocity distributions. And also the occupations numbers are per the debris space cell. The capital N is larger than the 1. And also we can calculate the coherence time by dividing the velocities again for the debris wavelength. This coherence time is quite longer than the oscillating frequency. And such ultralight bosons are motivated by the axion field or ALP action-like particle without the acoustic coupling or dilaton-like scalar. And the typical benchmark point is 10 to the minus 22 to 10 to the minus 20 electron volt, which can change the power spectrums for the kiloparsec or sub-kiloparsec scale. But above this scale, the power spectrums are same to the core dark matter. Still, the some 10 to the minus mass heavier than 10 to the minus 22 electron volt behaves like the wave like dark matter, but the power spectrums are similar to the core dark matters. And the lighter than the 10 to the minus 22 electron volt. This can interrupt the history of the cosmology. This cannot be the dark matters that are the recombinations, and it can be the early dark energy-like component due to the too light mass scales. It means that the mass scales are still smaller than the Hubble prediction term. The dynamics of such as colors are given by the following form, like as action, inflaton, or the quintessence of the dark energy. We can establish the actions for the scalar field in the expanding universe, and the given potential, we can expand the potentials in the quadratics and the chaotic term. And in the expanding universe, the equation of the motions are following through with the Hubble prediction term. When the Hubble prediction term is similar to the mass scale, the field value was frozen, and it behaves like dark energy with a slow rolling field. But when the Hubble prediction term is smaller than the mass scale with the quadratic potentials, then the pi field was lightest, and this behaves like the dark matter. And the equation is given by the omega equal to the juice, which is the matter-like, so the energy density reduces to the 8 to the minus 3. But in the general potential cases with the polynomials and power, the oscillation average equation of the state is given by the some functions of n, and for example, if the dominant term is given by the quadratic term, then the omega is given by the 2 over the 6, so the 1 over the 3, so the such a dominant quadratic scalars gives the radiation like the behaviors. And the initial values of the scalars that is given by the misalignment, like as action field. The initial field values that begins when the whole fraction term is similar to the its effective mass. And there might be the additional contributions for the such a field value and the productions. And if we consider the power spectrum of structure formations from this color field, not only the mass scale, but also we should consider the productions through this color field through the dark matters. If the wave dark matter is not solely the dark matters component, but there is another core dark matters components as a mixed one. And also not only the productions, the self-interaction strength is also important, which can affect the backgrounds and density perturbations. And also the isocurvature density perturbations contributions from impulsions is also important. So far we talk about just the dynamics of the background fields of the such ultralight dark matters, but we can also talk about the density perturbation, the fluctuations of this color component. For this, we will talk about the Blue's descriptions of this color field. In the non-relativistic regimes, the scalar fields can be written with the Schrodinger's Poisson descriptions with the complex color psi. Whether this psi satisfy the Schrodinger's equations with additional contributions from the gravitation of potentials, which satisfy the Poisson equations with an density of the mass. So, from the continuity equations and Euler's equations, we can obtain how the density perturbations delta grows over the cosmic history, and that there is additional gradient term from the their scales of the loose to supernova density, which gives the quantum projects. So such quantum projects arise from the gradients of the field, because this density laws includes the field values of the scalar. And if we taking just the first order, then we can obtain the perturbations equations, how the density perturbation delta evolves. There are the reflection terms, contributions from the expanding universe, and the third terms correspond to the gravity, and the final terms the contributions from the quantum project. So the gravities are biased to the quantum projects, make the density perturbation grow or oscillates over the time. And if there are sharp interactions of the color field, then this makes additional contributions for the quantum projects, so the effective genes wave numbers changes. So whether gravity term is large or quantum project term is large, this is determined the specific scale of the k, and this is given by the genes frequency. So if the quantum project is large, then the density perturbations oscillates, but if the gravity is large, then the density perturbations exponentially grows, and eventually it can go to the nonlinear regime. But before going to the nonlinear regime, we'll talk about the linear case. This can be represented by the transfer functions. In the ultralight dark matters, the path spectrum is different with the cold dark matters, and this is represented by the transfer function, this case of the k. The transfer function go to the 1 at the small k. Small k mean that the scale is very large. So this is the power spectrum for the cold dark matters, but in the ultralight dark matters, the power spectrums reduces in the large K. This means in the small scale, the power spectrums are surpluses. And such a surplus, the scale, the half modes of the power spectrum, one that is scales equal to the one half. This is called the cutoff scale. And the cutoff scale should not be too large, because there are observational results of some specific small scale like the Lyman alphas or the halo structures. In the mixed model with the cold dark matter and the white dark matter with the specific productions, the subproduction is weaker because the contributions from the cold dark matters are included. So the constraints for the such as small scale structures for the power spectrum subproductions should be interpreted with not only the mass scale but also the productions, and if we consider the interaction terms, then the constraints also can be changes. And there is also the non-linear regime. In the non-linear regimes, there might be the interferences of the wave-based field, and each field can be superposes each other through the different phases. So we can light such interference with the superpositions of the different plane wave, the frequencies and the wave number. And the superposition term, the cross term of the amplitude, wave numbers, and the frequency and the pace. And such a cross term makes the can make the distinct phenomena like as some ripple and some sparkle and the granule, some specific patterns of the wave dark matters. And the characteristic scale is given by the momentum difference, which is the reduces to the debris wavelength. And also the such a wave dynamics can make the self-gravitating bound states, even though there is no self-interaction term. The gravitational force can make the scalar field going to the inward, and this make the solitonic core. This can be described by the already mentioned the Schrödinger-Poisson sequences, because it includes this already the gravitational potentials. The simple for the simple dimensional analysis, we can calculate the calculations, the energy scale contributions from the momentum, and energy terms comes from the gravitational binding one. And the total energy is given by the summations of the momentum contributions and the gravitational one, and the minimizing of energy keeps the typical equilibrium size of the solitonic core. And also we can connect the wave dark matter to the other particle field. First of all, there might be the self-interactions between the different multi-scalar field, like as the motivated by the axibus. There might be the several possible self-interactions, like as the Cortic portal term or axion cosine portal terms, like as the pipe A. And such self-interactions can make the also the repulsive and attractive interactions and modifies the power spectrums and the solitonics of that. And also the such ultralight scalars can couple to the scalar field, like as the axion models motivations. The typical ultralighting field frequency is given by the dark matter mass, and amplitude is given by the functions of the local dark matter densities and mass scale. And the typical current field times given by also the mass and velocity. And there are several constraints and observational argument for the ultralight dark matter, but through what already mentions, the power spectrums are processed in ultralight dark matter, and for the small scale, and there's a specific cutoff scale. The observations comes from the Lyman status or Halo abundance and the classic statistic, and this should be the analyzed with the productions together. And also the non-linear regime, the solitonic cores, like as a dwarf galaxy, there might be some internal structures in the such compact objects due to the scalar field. And also in the early universe, too small and ultralight mass scale can interrupt the history of the cosmology, like as impacts on the CMB or the gravitational lensing. And also the isochromatic contributions from the inflationary initial conditions should be the constants. And recently, the black hole palladiums is also important topic. The rotating black holes can lose the spin, and this makes the scalar field cloud by the growth of these occupation numbers around the black hole. And this can exclude the specific mass ranges depending on the stellar black holes or the extremely heavy black holes. And also we can talk about this total coupling between the wave dark matter and standard model particle with the lab and the precision test to prove. There might be the oscillations of the specific quantity like other mass or the structure constant, and the equivalence principle violations with the both test, and some spin precautions and several electromagnetic quantities like as the axions experiments. So so we talk about the overviews of the wave dark matters. There are many candidates of dark matters, but such ultralight mass scale can be the other approach, especially motivated by the action, and this show that some characteristic behaviors of the oscillating wave pictures, and this can be described by the equation of motion for the background fields, and the equation of ties the difference for the what is dominant term in the potentials. And also we can talk about the density perturbation by considering the fluid descriptions and Schrödinger's Poisson equations, and this determine the past spectrums how the difference to the core dark matters, and especially the small scale this density perturbations are surplus. And also in the non-linear regimes, the solitonic cores can be pierced by the gravitational bound, and several constraints from the cosmological laboratory observations can bound some specific wave dark matter mass productions around the coupling.